We are usually familiar with constructions that turn a polygon into a square of equal area. But what about the reverse? Turning a square into regular polygons with the same area. Have you ever thought about this? Imagine a square with each side equal to 1. Now try constructing an equilateral triangle using only a straight edge and compass. It is always possible to transform a polygon into a square of equal area. You can divide a polygon into triangles, turn those triangles into one big triangle, then convert that into a rectangle, and finally into a square. We use the geometric construction to change only the shape continuously while keeping the area the same, a process called unequal area transformation. So, can you apply the same method to this problem as well? Turning a square into an isosceles triangle is simple, but turning it into an equilateral triangle? That's not simple. I've tried every method, but none of them worked. It even made me wonder, is it impossible to construct that triangle? But in this case, the construction is possible. That much I can tell you for sure. Why? The square's area is 1. Here's the area formula for an equilateral triangle. We want this area to equal 1. So we solve for a. Now look at the number a. It's simply 2 divided by the fourth root of 3. The formula includes a fourth root in the denominator. If we can construct this length, then we can construct the entire triangle. Let's see if this number is actually constructible. The numerator 2 is a rational number, so it's constructible. The denominator is the fourth root of 3, which is the square root of the square root of 3. The square root of a rational number is constructible, and the square root of a constructible number is also constructible. Therefore, the denominator is constructible as well. A is the quotient of two constructible numbers. Since arithmetic operations on constructible numbers are themselves constructible, A is also constructible. In theory, we can construct A from a single unit length. Let's actually construct it. The numerator 2 is easy, just double the unit length. For the denominator, we'll start by finding root 3. Draw one line segment of length 1 and another of length 3. Use that as the diameter of a circle. Draw a perpendicular through this point. The intersection gives you root 3. To get the fourth root of 3, using the length of root 3, repeat the same square root construction once more. Now we have both 2 and the fourth root of 3. Using the standard division construction, we can find the length of this number. This is 2, this is the fourth root of 3, and this is the side length A of the equilateral triangle. With that length, draw two circles like this. Connect the 3 points. You get an equilateral triangle. You can always construct an equilateral triangle with exactly the same area as a square. Now, what if we take one more step? Can we construct a regular pentagon with the same area as a square? For a regular pentagon, the area formula is this. We want this to equal 1, so the side length A must be this. The question is this length constructible? Let's find out. The numerator 2 is rational, constructible. Look at the denominator. That's the fourth root of this number. We call it b. Since root 5 is constructible, b, which is made by adding and multiplying constructible numbers, is also constructible. And if b is constructible, the square root of b and the square root of the square root of b are constructible as well. The denominator is constructible too. Now, look at the number a again. A is simply a division of constructible numbers, which means A itself is constructible. Therefore, you can find the length of A using the same geometric techniques we used for the equilateral triangle. Once you have that, you can apply the standard construction for a regular pentagon. The result is a regular pentagon we want. We've constructed an equilateral triangle and a regular pentagon. But can we do it through a pure equal area transformation without calculating the side length? That's a different challenge. If you know a simpler construction or have any insights, please share them in the comments below. Thanks for watching, and don't forget to like and subscribe. Thank you.